And let me make this full screen. All right, everybody. Welcome to the last lecture in steel design this semester. Couple quick housekeeping items. So as of a minute ago, like literally a minute ago, if you check the course content section on Blackboard, you will find that the remaining 2 homework solutions are posted. So homework 6.7 is posted, as well as homework 6.8. Now, if you remember, homework 6.8 was due today. So there's no way it's going to be graded, like now. But I want you to have that solution because that might be covered on the exam. And so I posted that solution just now, but as a result, I can't really accept late submissions on homework 6.8 because you have the answer right now. So the point is, every single homework is graded other than the last 2. My TA is going to work on grading those next week. So the only outstanding assignments in this class are, or in terms of grades, are homework 6.7, homework 6.8, the bonus assignments, and the final, and that's it. So the attendance grades are up to date other than today's. So as soon as today's grade, or as soon as I process today's attendance, I'll get that posted. Sometimes the way that Blackboard works, sometimes that we might end lecture at 11:50, but the attendance report doesn't populate until like a couple hours later. I don't know why, but it just sometimes takes a while. But I'll post that as soon as it's available. If you look here on the slide, you'll see the grade breakdown. So the attendance is worth 5%, the homework, the 3 exams. I also, if you go to Microsoft Teams, you'll see I posted that at-home game spreadsheet because I know everybody's, it's always, a question, what do I need to get on the final to get a certain grade? Well, that spreadsheet will do it for you. So if you input your grades, it'll tell you, what you need to get. I for those of you that had me for structures last semester, I did the same thing in there. As for the remaining surveys, for the course learning outcome survey, the one that's on Google Forms, I think everybody did it. I didn't have everybody upload, but I think everybody completed it because I have 21 responses and there's 21 people in the class. So I will probably just give everybody 5 points for that. For the university administered one, there's still 4 people that haven't done it. So again, if you haven't done it, please do it. Again, you can say I'm the worst professor ever, but it's free points. And if you have any honest feedback, I'd really like it. With that, let's get right into the final and talk about what's going on here. So it would help if that advanced the slide. Give me a second. Okay. So just like we've done in previous exam reviews, I'm going to talk about the logistics, and then I'll talk about the content, the topics on the exam. The logistics, I want to be clear, are no different than any of the other exams, except for one thing, is that you have another hour to do it. To be clear, the exam is designed to be 50 minutes long. It's not designed to be a longer exam just because I have 2 hours. Honestly, I just treat this like any other exam. So the exam's going to open on Tuesday. It's going to open at 10:15 a.m. and it's going to close at 12:15 p.m. And it's designed to be 50 minutes long. The way the exam works is the way that all the others have worked. There's the timed exam, and then there's the upload form where you can upload your scan of your computations. I'm giving you another hour on that, so that'll close at 1:15, so you won't feel rushed. But I've been teaching this class for a long time, and usually what I've found is that nobody really feels rushed on the final anyways. When we do this in person, when we start the exam, let's say at 10:15, by an hour, maybe an hour and a half into it, most people are already done. So it's usually not a time crunch issue. Like I said, we're doing it that time slot because this class meets Monday, Wednesday, Friday at 11, and so that's Tuesday at 10:15 a.m. So that's why we're doing it then. As for the operation, it's the same thing same with all the others. It's a forced completion, so once you start it, you have to finish it in one sitting. It'll auto submit after 120 minutes, not 60 minutes, because we got the 2 hours. The questions appear all at once, so you can review your responses before submitting. The manual, we're doing this online, so it's open book, open notes. You can use the manual. You definitely should be using the manual. You'll need it. I think that's pretty clear. I think of all the exams that we've had in this class, if there's any one exam where it's absolutely desperately necessary that you have the manual, it's this one, because the beam charts, the ZX tables, all that stuff, you need the manual for that. All the resources that are on Blackboard are available to you, the recordings, the lecture notes, the exams, all that, not the exams, the homework solutions. The one thing that I ask, it's the same thing I've been asking all semester, just don't give or receive aid from another individual. And so that includes anybody else in the class, forums, Chegg, all that stuff. You've got more than enough resources to address the exam on your own, and I find it easier to just do it on your own anyways. Same format, 4 to 5 short conceptual questions, no more than a sentence or two answering them, and then 2 to 3 computational problems. Again, do me a favor and type out an answer for every question, even the computational ones. It really helps me out with the grading. So if it's a design problem, just type in, W27 by, 84, whatever the shape is. You could just do that and it'd probably be fine, assuming that's what I asked for. If I say, select the most economical shape, you can just type the shape in. It'd make my life a lot easier. Make sure don't just answer the question on your scratch work. Again, type it out. Let's talk about the topics. So this is the columns and beams exam. That's what we're doing on this exam. So for columns, make sure that you understand the basics of the concepts, basic buckling theory. What's the deal with an effective link factor? Those are the K values. Geometric imperfections, residual stresses, just the concepts. Make sure you get what's going on there. Strong axis, weak axis, all that stuff. In terms of computations, you got to be able to analyze and design. So analyze a column using either the column curves, that's the stuff in chapter E, the 0.658 and all that, raise to the FY over FE and all that, or table 4.1, because remember you can use table 4.1 for analysis and you can use table 4.1 for design. In fact, it really is the only way that you can design because you use that to select a shape. For beams, make sure that you understand, again, the concept. So with beams, we're talking about, what's the deal with the elastic neutral axis versus the plastic neutral axis? What is the deal with MP versus MY? What is ZX? All of those concepts. Make sure you understand LTB, understand moment gradient, the CB term. What is CB doing? Make sure that you can analyze and design continuously braced beams and discretely braced beams. So with continuously braced beam design, you're using table 3.2 to select a section. With discretely braced beam design, you're using table 3.10, which is the beam charts. That's where you're going like that and then finding the shape. Make sure that you can also assess deflection limits and all of that. And that's basically the exam. That's what we're doing. Everything else that's in this presentation is designed so that you have everything that you need, at least from a formula and equation standpoint, all in one spot. So, don't forget the K values for analysis and design. That's the table in the commentary in the back of the manual. And remember, we're using the recommended values, not the theoretical values. When it comes to analysis of columns, we have the first method, which is section E3. That's the AISC column curves. That's just computing the capacity directly. And then analysis method 2 is to use table 4.1, or specifically 4.1a. 4.1a is the table for 50 KSI steel. Keep in mind, you're probably going to have to use linear interpolation, so make sure you have that just handy. For column design, we factor the load. We determine the largest KLX and the largest KLY for the column. And then based on KLY, we select a group of trial sections, so at least one W14, one W12, one W10, one W8. And then for each of those sections, we see whether or not they're going to work. And so we check their strong axis capacity. And so we might have 4 trial sections, and of those trial sections, maybe 3 of them work. And of the 3 that work, select the lightest one. So if you want, you can organize them by their weight. And as soon as you get one that works, it's good. Make sure, though, at the very end that you analyze using method 1 to verify its capacity. Definitely a good idea on the exam, since you're in a timed pressure environment. Make sure that you're analyzing it to see if you get the same answer. For beams, make sure that you know what's going on with MP, what's going on with ZX. ZX is basically just that section property where you start off by finding that imaginary line where the area above equals the area below. That's the plastic neutral axis. And then some moments of each area times the distance between the centroid of that shape to that imaginary line. And just do that for all the areas, and that's ZX, multiply it by FY. Boom, there's your MP. If it's a continuously braced beam, the capacity is going to be limited to, or it's going to be MP. That is the capacity. It's not limited. It is if it's continuously braced. So we can look up that capacity based on what's listed in table 3.2, but we can also use that table for design. Remember, they're all grouped, so we find our required phi MP and pick the bold row because that's the lightest section. Table 3.3 would be what we would use if we are governed by deflection requirements, which is very possible. So if we find that we have enough moment capacity and enough shear capacity, but we're failing in deflection, abandon table 3.2 and just select the section based off table 3.3, because that's what's controlling what element you're picking. Again, similar grouping. You pick the bold row. Table 3.10, that's your design aid for LTB. Remember, you go in on the x-axis with LB, the y-axis with your MN over CB, and then you select the lightest shape. Again, go up to the right, solid line. For continuously braced beam design, you start off by computing the factored moment, and then compute your required IX based on your deflection limits. Don't forget that 1728 conversion factor, and don't forget to incorporate a beam self-weight. Again, a good value somewhere between 50 and 100 pounds per foot. After step 2, you should have a required moment and a required moment of inertia. Then we go into the table 3.2 and select based off of phi and P. That's if it's continuously braced, okay? Check the deflection requirements. If deflection requirements don't work, you go off table 3.3 and then analyze your section. Analyze for moment, for shear, and for deflections. Moment gradient modifier, that's the CB term that we've got to adjust our buckling capacity for. Remember, a lot of these CB terms are computed for you. They're listed in table 3.1. But if you got a wonky loading and you need to compute CB, you can do that using the following expression. You just got to break out your statics, break out your structural analysis, and compute quarter point moments and the maximum moment within a given unbraced segment. There's your LTB equations for capacity. Again, all in one spot for you. And then there's discretely braced beam design. The big thing to keep in mind with continuously braced beam design versus discretely braced beam design is that the process is basically the same. The only difference is that you're using a different aid. Okay, instead of using table 3.2, you're using table 3.10. Finally, analyze it just like you did before, and that is basically it. I put this little table in here for the example that I pre-recorded in case you wanted to copy the format for a later or for while you're on the exam. But that's it. That's it in a nutshell. So I'm going to stop. We'll go back to like this right here, and the floor is yours. If anybody has any questions, feel free to turn your mic on, to put something in the chat. Floor is yours. Yes, sir.
I'm trying to pull up the table with the loading that we needed to use for the homework that we submitted today with the compact and subcompact.
Okay.
Can you remind me which table that is again?
It's table. It's on 16.1-16. Or, well, I guess 17, but it's in chapter B. It's B41A. There's the B41A is the table for columns. Table B41B is the table for beams.
Okay. Do you think you could briefly go over real quick the discrepancy, or rather the convention that we use for determining which equation to use, subcompact or non-compact or compact, when evaluating the capacity for I-shape?
So All right, give me 1 sec. The easiest thing to do would be to pull up that set of lectures because the tables are all in one spot. Give me 1 second. Okay. So this should be what you're looking at in the manual right now. Is that correct?
Yeah.
Okay. So first off, there are 2 tables, okay? I know that it looks like there's 3, but the second table just takes up 2 pages. Like the first table is for columns. That's where it says axial compression. And the second is for beams because it says flexure. Okay, so does that make sense? So the first point to keep in mind would be if you are assessing a column, don't look at the other 2 pages, right? That it doesn't matter, right? If you're assessing a beam, don't look at the first page. So far, so good?
Yeah.
Okay. Now, next thing to do is let's say we're looking at a column. Let's just keep that simple, okay? So if you're looking at an I-beam, okay, like a W shape, let's just pick a shape out of the clear blue sky, okay? So let's pick a W10 by 49, okay? So we're going to treat it as if it's a column, okay? So the first thing that we need is the BF over 2TF. And let's just look at the flange for now. Let's just look at the flange. So we need the BF over 2TF for a W10 by 49. So if I go to page 1-28, 1-28,
8.93.
8.93. Okay. All right. Now, a flange. Is a flange an unstiffened element or a stiffened element?
Unstiffened.
Unstiffened because it's only supported on one side. That's absolutely correct. So what we're going to do is we're going to look up the unstiffened elements. So if you look at the table is sort of split up like right here. So everything above that is an unstiffened element and everything below that is a stiffened element. And so then we have to identify which case we're looking at. So for instance, we're not going to look at case 4 because case 4 is looking at the stems of T's. Like we're looking at a W shape. So it's not case 4. It's not case 3 because case 3 is looking at angles. It's not case 2 because case 2 is looking at built up I-shaped sections. That's like actually taking a plate, and welding it together. That's not what we're doing here. We're talking about a rolled section directly from the mill. So we're going to be looking up case 1. Okay, case 1 says that our limiting slenderness, and I'm going to call it lambda r. I'm calling it lambda r because that's what it's calling it here. And I'm calling it lambda rf because we're looking at a flange is 0.56 square root of E over Fy. Okay? Now, when you chug that out, you get 0.56. Now, let's say it's 50 KSI, just for ease of discussion. Ends up being 13.49. Okay, with me so far?
Yes.
Okay, so if you want a simple way of looking at it, let's say that this is like a number line looking at slenderness, okay? And this is 13.49. Everything on the left side of this line is compact. Everything on the right side of this line is slender. And your slenderness for the W10 by 49 is right there, 8.93. So are the flanges compact or slender? They are compact. Does that make sense?
Yeah.
Because their slenderness is less than that limit. And that limit basically is the dividing line between compact and slender. Now, in order to fully answer your question, first off, are you okay if I erase some of this ink?
Yeah.
Okay. So for beams, it's a little different. Okay, with beams, you have a lambda PF and a lambda RF. Okay, and if you're in this range, you're compact, you're non-compact. If you're in this range, and you're slender if you're in this range. And that's just how beams are. Beams have 3 ranges, columns have 2. And so what you're trying to do is figure out what range you're in. Okay, so as an example, if I look at, let's say, the homework that you just did, okay, let me find that solution right here. So you should have gotten that this is 9.15, right? And then the lambda R is, I think, 24.1. Is that correct? Is that what you got? If you're saying something, I can't hear you.
I'm pulling it up right now.
Okay. And just so you're aware, what we're doing is we're saying, okay, we're looking at beams, okay? So the left table is for unstiffened elements. The right table is for stiffened elements. And so if I'm looking at the flange, there's your lambda P. There's your lambda R. Just right there and right there. So what did we just get? What was the, we were looking at a W10 by 49. A W10 by 49 has a flange slenderness of what? What was it? Was it like 8.93?
That was 8.95, but that, okay, so whether we go with okay, so we need to know like where 8.95 falls within that range of values.
Exactly. So think of this as a number line, right? 8.95 is going to be like right here, right?
Yeah.
So that means that this flange is compact under this criteria, right? But on that note, okay, what if I had a BF over 2TF of like 14.6, right? Well, that would be that'd be like right here, right? So that'd be non-compact.
Okay, I think I understand now.
All you're doing is you're looking at how, for lack of a better word, how flimsy your flange is, and just trying to figure out what range it falls under. Like, that's it.
Okay, I got it.
All right, does that make sense to everybody else? Is there anybody else that has a question about that? So since the solution to the homework is up, I'll go ahead and pull it up. Let me share this. So let me move this over here. So this is the solution to the last homework that you just submitted. And so we were looking at a W14 by 43. And so if you look at the compression for columns, this is the BF over 2TF, and this is the limit, right? So this is less than that, so the flange is compact, right? But on the web side, here is the web slenderness, and here's the slenderness limit. So the web is more slender than the limit. See what I mean? The web is flimsier. It falls on the other side of that line. So that's why we have a compact flange, but a slender web. And if we look at the bending side, here's the flange slenderness, and this is lambda p. I didn't even bother computing lambda r because for both of these instances, these are less than the lambda p. So we know that the flange in the web is compact under bending. So what's your answer? Here's your answer right there. The flange is compact under compression, and it's compact under flexure. But for the web is compact under flexure, but it's slender under compression. That's the dividing line there. Does that make sense? Okay, good. Anybody else? And if you got other questions, please, throw them out there. Don't let me off easy just because it's the last day. You can always turn your mics on if you need. Well, that's the point. That was the reason I started doing all these daily assignments. I don't believe he's here today. Believe he let me know in advance, though. It's okay. But yeah, but I got 17 people here that have hopefully got 17 sets of questions. Well, thank you. I appreciate that. Sucks we haven't been in person, but Steel Design's my baby, so I love teaching this class. Well, I can appreciate that too. I'm a fan of their coffee. I like their coffee. It's a simple thing to enjoy there, but I like their coffee. Although I'm having tea this morning. I'm having a cup of Earl Grey. Any questions about columns? Like, let me sort of probe the class a bit on that because it's been a while since we've done columns. Just to, kind of ask try and lead some discussion. Let me turn off my. I thought I closed that. Let me turn off my. Can we review KL? So let me pull this up. Give me 1 second. Okay, so first off, there's a couple things to take away when it comes to KL. First off, make sure that you're using the recommended values for design and analysis and not the theoretical values. Nothing in this world is perfectly fixed. Nothing in this world is perfectly pinned. So the theoretical values, which assume perfect fixity or perfect flexibility, need to be tweaked a bit to account for the real world. So that's why there's a difference. And usually what that means is that, so there are some instances where K stays the same, but usually K is having to increase a bit, okay? And the one thing to keep in mind whenever you're looking at columns or beams is that try and think how changing a given term is going to affect the answer at the end of the day. For example, if I have a column, I'm going to ask the class this, but if I have a column and I keep everything exactly the same with that column, but I increase K, what does that do to the capacity? So if K goes up, you're saying the capacity goes up. Right? So down. So if K goes up, the capacity goes down. I want you to tell me yes or no, like what with confidence. All right. So let me ask you this, okay? If K goes up, KL over R is going to go up, right? Okay. KL over R is the slenderness, right? KL over R is a measure of how slender the column is. And as slenderness increases, capacity goes down. KL over R is a measure of how flimsy your column is. The bigger that number is, the more flimsy it is. The more flimsy it is, the less it can hold up, right? So if your K goes up, your capacity goes down, okay? That's some of what we're talking about here. A lot of the concept issues can be resolved by just thinking about some of these thought experiments. Like what happens to a beam if you increase its LB? The bending capacity goes down because LB is a measure of the distance between braces. The farther apart those braces get, the flimsier the segment is because its quote unquote L over R is going up as well. So that's the first thing to keep in mind. Okay. Now here's the second thing to keep in mind. Let me get my little display here. And everything that we're talking about could be said for columns and beams too, kind of. When you're loading a column, what the column cares about is where is the highest slenderness. It's sort of like a path of least resistance, right? If I take this column and load it, it is going to buckle whichever way it wants to buckle. And the way that we can measure that is by looking at slenderness, by looking at KL over R. And so what we can do is we can look at this column and we can say, okay, this column has bracing this way, so bracing that keeps it moving from left to right, but it also has bracing this way that keeps it moving up and down. So if I'm looking at it like it's a column, bracing that prevents it from moving this way and bracing that prevents it from moving this way. And so along the x-axis and along the y-axis, I can break it up into a series of segments. I can say the x-axis might have 2 unbraced segments and the y-axis might have 4. I don't know. For each of those segments, I compute a KL over R. Whichever one has the highest KL over R, that's the one that's going to control how strong the column is. Because the largest KL over R means that's the segment that is the flimsiest. That is the segment that has the largest slenderness. As slenderness goes up, capacity goes down. Okay? Does that make sense? Okay. Now, I don't want to just stop talking if I haven't fully answered your question, though, because we could talk about a lot more. I just want to make sure I'm getting everything. And if there's again, you can always turn on your mic if you need to like ask verbally. Sometimes that's easier. Okay. Anybody else? Anybody have any questions about columns, column analysis, column design, beam analysis, beam design? We got a lot of stuff on this exam, so I want to make sure that if there's any lingering topics, you let me know. I will give it another minute or so, and then we can go ahead and call it early. All right. All right. Last chance. Anybody has any questions? All right, everyone. So I think we're probably good unless somebody's working on a question or whatnot. You can always use the raise your hand feature or whatnot. But before we close it out, just a couple of housekeeping items. If you go to the excuse me, if you go to the very beginning of the presentation, there's still 4 folks that haven't done their university administered survey. So please do that if you haven't had a chance to do so. All the solutions are available on Blackboard along with the at-home game on Teams, so you can play the at-home game, figure out what you need to get on the exam to get a certain grade. Everybody should be clear on exam logistics, I think, at this point, because it's no different than any of the other exams. And with that, that's pretty much all I have. I said this last semester to my online classes, and I'm going to say it to you all as well. I am very proud of all of you. This has been, I know, a challenge. We were talking about this a little bit before class started, how I know that there might be some of you that are quote unquote over it with the online learning. I know it's been tough. I know that this has been probably not what you signed up for. And all I can say is that in response is that you all have met the challenge very well. In all honesty, nobody's really complained at all. And I think that says a lot to your character, and it speaks very highly of it. I will be around, for the day, the weekend. You can always reach me on Teams. I've got the Teams app on my phone if you have any questions as you're preparing. And with that, that's all I have. I think that you all have done very well this semester. I'm proud of you, and we have our final on Tuesday. I'll get that graded, as soon as I can. We have capstone presentations the next day, so I might be a little delayed on that. But other than that, that's all I have, everybody. Great job. Best of luck on the final and your other finals as well. And here's to hoping that we are back in person in the fall. So looks like that's the plan. So got my fingers crossed, as I'm sure many of you do as well. That's all I have, everybody. I will see you all there for the final. And if I don't have a chance to chat with you, I hope you have a very relaxing and productive summer, and we will see you in August. That's all I've got, everybody.